From what we have discussed before, we know what holds an atom together. That's like a tiny nucleus and the electron cloud around the nucleus. What holds the electron cloud to the atom is the Coulomb force, the attraction between the proton and the protons in the nucleus and the electrons in the electron cloud. Each of the electrons is going to be subject to this force FkQ1 Q2 over R squared. Of course, the electrons are also affected by the Coulomb force due to the other electrons, but we are not getting into this here. Let's focus now on the nucleus. This tiny nucleus here is going to have protons and neutrons. Now, these protons are going to be in that tiny space that's the nucleus. And they are going to be subject to that Coulomb force. Any proton is going to repel the other protons that are within the nucleus. For example, if we look at the schematic here, the red ones being the protons, this proton here is going to be affected by this one and this one. Both of them are going to repel it. And that repulsion force is going to be quite huge because R is quite tiny. Remember, it's 1 over R squared. So having a small r is going to result in a large force. So one might ask, how come the nucleus stay together despite that large force? What holds the nucleus together? The answer is what we call the strong nuclear force. The strong nuclear force is a force between nucleons that are protons and neutrons. Protons attract other protons through the strong nuclear force. They attract also neutrons through the strong nuclear force. Similarly, neutrons attract other neutrons with a strong nuclear force and attract protons with a strong nuclear force. Neutrons have only attraction towards other neutrons and protons. However, protons, in terms of their interaction with other protons, they have a dual personality. They attract with a strong nuclear force and repel with the Coulomb force. Now, the strong nuclear force is strong enough to overcome the Coulomb repulsion. It has to be strong enough to overcome it for the proton to stay within the nucleus. However, it acts over a very short distance. The size, not really of a nucleus, the size of an average size nucleus. Large atoms, if I have a large nucleus like an uranium nucleus, a proton at this end is not going to affect through the strong nuclear force a proton at this end. Two atoms, for example, don't feel the strong nuclear force from each other. That's any size atom. Now, let's explain this a little bit more. If we look here at the schematic, the black dots being neutrons and the red ones are protons. Each red dot is going to be affected by all the other red dots. All of them are going to repel it. So the overall force acting on this one, for example, is going to be the sum of all forces or repulsive forces due to all the other protons. On the other hand, it's going to be attracted by the strong nuclear force by all nucleons that are close to it. For example, these three here are going to attract it pretty well. This one here also might attract it pretty well. This one is going to attract it, but not with a strong enough force. The balance between these forces is what holds that proton in place within that nucleus. Now, you can lose that balance by extra energy. For example, if that nucleus is going to absorb light or if it's going to be hit by another particle, that balance is going to be lost. What you need to consider when we have a large nucleus, like uranium, for example, we have a lot of protons there. So each proton is going to be affected by a lot of other protons. So it's going to be more difficult to balance that repulsive force. It's going to be a very shaky balance, and that's why uranium is going to be radioactive. Now, that shaky balance is what's responsible for all the decay of nuclear elements.